This video set is on introducing inter versus intramolecular forces, bond polarity, reminding us of that, and then reminding us of molecular symmetry and what causes a molecule to be polar or nonpolar. So what holds things together? Intramolecular forces hold particles together within the molecule, so covalent or ionic bonds. So if I'm looking at a water molecule here, the bond between an oxygen and a hydrogen is called an intramolecular bond because it is within the molecule. Versus an intermolecular force causes attraction between particles. So these are molecules, ions, or atoms of a substance, and so this is between two different molecules here. So this ... represents a bond, and I put bond in parentheses because it's not necessarily a true bond, but it's still an attraction that requires energy to actually break apart the molecules. And hopefully this is not new information because you just did a lab where you were studying the energy and the forces of different molecules as they were attracted to each other. So, the four intermolecular forces are ion dipole, dipole-dipole, London dispersion forces, and hydrogen bonding. So, we've actually learned three of them. We've learned these three. The ion dipole is new. So, the ion dipole is between an ion and a polar molecule. Most of the time it's going to be between an ionic bonded salt and mixed with water most of the time. Dipole-dipole forces are between two polar molecules. London dispersion forces are between two nonpolar molecules. And hydrogen bonding is between a hydrogen and the lone pair on a nitrogen, oxygen, or fluorine on another molecule. So these nitrogen, oxygen, and fluorine will all have lone pairs generally on them, and so a hydrogen will be attracted to those lone pairs. So the strength of these molecules is that an ion dipole is the strongest, the hydrogen bonding is the second strongest, the dipole-dipole is the third strongest, and then the London dispersion force is the weakest. So electronegativity relationships between atoms ultimately determine the nature of bonding. So remember our bright yellow electronegativity periodic table where we had our Vesper shapes on the back? We'll need to be able to remember kind of how to do that because we're going to be able to look at our type of electron sharing, whether it be polar or nonpolar or ionic, to be able to figure out the type of intermolecular force present. So if I've got an equal electronegativity, that means I'm going to have equal sharing. If I have an unequal sharing or unequal electronegativity here, that means I have unequal sharing. This is just symbolizing that there's a slightly positively charged molecule, and this is symbolizing that there's a slightly negatively charged molecule. If I have electron transfer, that means that I have created an ion, so there's a positive and a negative ion there. So if I have equal sharing, I know that that's a nonpolar covalent bond. If I have unequal sharing, I call that a polar covalent bond, and electron transfer is an ionic bond. The elements involved in a nonpolar covalent bond are two like nonmetals, so for example, hydrogen. So a lot of our diatomics, remember, were our nonpolar covalents. An example of an unequal sharing is two unlike nonmetals, so for example, water. And an example of an ionic bond is between a metal and a nonmetal, for example, sodium chloride. So bond polarity, because of a difference in electronegativity, polar covalent bonds have a shift in electron density. So there's a permanent unequal distribution of electrons due to different electron pulling power. So in this case, my fluorine, which I know is the biggest bully on the periodic table, is going to actually pull the electrons more towards it, so it has a slightly negative charge, and the hydrogen then would have a slightly positive charge. And so the hydrogen has lost some electron density, and the fluorine has gained some electron density because of the high electronegativity of fluorine. So electronegativity differences between atoms combined with molecular shape, it determines if the whole molecule will be polar. Molecules are polar if they contain polar bonds, and if the polar bonds are asymmetrically arranged around the central atom. So polar bonds, remember, means unequal sharing. And when it's asymmetrically arranged, think polar bears look different. So when molecules do not look the same, they are considered polar. So polar bears look different is going to come back into play. So molecule polarity here, so if I have polar bonds, I'm going to have asymmetrical geometry. If I have polar bonds here, but if I look at my molecule, okay, it looks the same on all the sides, so I would have symmetrical geometry. Here I have polar bonds, but this does not look the same on all the sides, so I would say asymmetrical. And our good old carbon dioxide, let's not forget our Vesper theory electron dots over here. We're going to have symmetrical geometry because it looks the same on all the sides. So, because it's got asymmetrical geometry, this would be a polar molecule, showing a slightly positive side on the hydrogen and a slightly negative side on the oxygen. So these are what I mean by lone pairs on a nitrogen, oxygen, or fluorine on another molecule. So this is kind of what I'm talking about here. Because this has symmetrical geometry, it would be considered a nonpolar molecule. And because this has asymmetrical geometry, this would be a polar molecule, again showing the electron distribution. Even though this is asymmetrical geometry and a nonpolar molecule, I can still show the electron distribution being slightly different, but it's slightly different on both sides. Okay, there's your kind of introduction to molecule polarity and intermolecular forces affecting molecule shape.